Welcome back, everybody. Let's continue our discussion of section 6.6. I want to do some examples having to do with problems with rational exponents. The primary thing we're really going to be doing in this section is simplifying expressions that have rational exponents. And this will be very similar to all of the simplification we've already done, especially with expressions involving monomials and polynomials. So we're really just dealing with exponents here. The first thing that we should remember, and I think one of the key points, is that we want an expression with no negative exponents. We remember this from polynomials as well. If we have negative exponents in the numerator of a fraction, that means that we actually have those powers in the denominator of the fraction. So let's just put them there where they belong, and vice versa. If we have negative exponents in the denominator, those things really belong in the numerator. The thing on which we're really going to spend most time in this section is this second rule. We want to make sure that we only have positive integers as exponents in the denominator. And that comes from this simple rule. Since rational exponents are roots, if we have them in the denominator of a fraction, that means we need to rationalize the denominator. So we're often going to solve this problem by rationalizing. And we'll see a couple of techniques for that. This last rule we'll see is also pretty important, and it usually comes about naturally in just simplifying the expression itself. But we don't want any indices of radicals. That is, we don't want to have any nth roots that are larger than they need to be. We don't want to have a fourth root in an expression when it could be a square root. This is a pretty simple example. Let's say that we were looking at the fourth root of 9. Of course, we should recognize here that we can convert this into a rational exponent, 9 to the 1/4. But 9 is itself already a square. So we can rewrite that 9 as 3 squared to the 1/4 power. This actually gives us the opportunity to reduce the exponent on 3, because we have 3 to the 2nd power that's then raised to the 1/4 power. So we need to multiply these exponents. That gives us 3 to the 1/2 power, which, if we want to convert back into roots again, is just the square root of 3. So this is what your book means when it wants you to have the least possible number for every index. In this problem, we reduced our index from 4 down to 2. All right, with those thoughts in mind, let's move along and have a look at some examples. The first kind of problem you'll see is a pretty simple one, where all we're trying to do is figure out how to combine rational exponents. Well, in this case, we already know that when we have the common base raised to different powers, we can just add those powers. This becomes p to the 10/4 power. Now, just like with any other fraction, we can certainly reduce this one as well. This is the same as p to the 5/2 power. And if we wanted to translate that back into root notation, that would be the square root of p to the 5th power. So the rules of exponents come into play pretty quickly here. Let's say we have some number b raised to the negative 5/6 power. We've talked about this a few times already. That negative 5/6 just means that we have the reciprocal of b to the 5/6. But here's where we really have to start playing the game of simplifying denominators. Because that negative 5/6 power means that we have a radical in the bottom of a fraction. We can write this, which means that we have a 6th root of b to the 5th in the bottom of this fraction. Well, this is a little bit problematic for us because we know we need to have a rationalized denominator. As a note, though this isn't the way we're going to be doing the math, we can look at this way as well. That would be a style we're a little bit more familiar with at this point. But when we write this expression in root form, it makes it very clear that we have a radical on the bottom of this fraction, and we need to rationalize that. But in rationalizing this denominator, we see that it's actually a lot simpler to work with this format. Because our goal in rationalizing the denominator is to end up with a denominator that has b to the 1st power in it. That's where we'd like to get. Well, that's pretty easy when we think about the regular old exponent rules, because we're going to multiply the top and bottom of this fraction by the same thing, so that we can multiply it by 1 in a special form. But in the denominator, we're going to add the exponents on b. So the exponent we're looking for in that new factor is going to have to add with 5/6 to give us 1. How about we multiply by b to the 1/6 divided by b to the 1/6? At least this way we know we're multiplying by 1 and not changing the value of this expression. But when we do the multiplication, 1 times b to the 1/6, well, that gives us b to the 1/6 on top. But b to the 5/6 times b to the 1/6, we need to add those fractions. That gives us b to the 6/6. And 6 over 6 is 1. So that leaves us with just b to the 1/6 in the numerator and b in the denominator. If we want to rewrite this in radical form, that's the 6th root of b divided by b. I think this is a really important problem, and I hope you'll go back and take another look at it. But the point here was trying to rationalize a denominator where we knew we had a radical there. I'll leave you with one to try on your own. What if we had the expression r raised to the negative 4/5 power? The process of simplifying this is pretty much the same, and the answer you should come up with is r to the 1/5 over r. Give this a try and see if you can make sense of it. Speaking of rationalizing denominators, when we are dealing with just numbers and not variables, often we can really simplify an expression a whole lot when we have a denominator that contains a radical. Let's look at an example of that. Well, neither the numerator nor the denominator of this particular example are easily simplifiable. I have no idea what the 4th root of 27 is, and I certainly don't have the square root of 3 memorized. But maybe there's a way we can take this down into a much simpler form. And part of that's going to have to be rationalizing this denominator, because we can't keep the square root of 3 on the bottom of this fraction. How about we convert everything into rational exponent form? That would be 27 to the 1/4 over 3 to the 1/2. There's a key insight to this kind of a problem, and it's that the 27 and the 3 are related to each other here. In fact, 27 is 3 cubed. So let's see if we can simplify this by making the base in the numerator and the base in the denominator the same. Because when we have like bases, that allows us to use the exponent rules that we know. Adding exponents, subtracting exponents, multiplying exponents. So if we can get 27 in terms of 3, that's really going to help us simplify this problem. So 27 in terms of 3, well, that's 3 cubed. Now we have that raised to the 1/4 power. All of that still over 3 to the 1/2 power. Now we've got common bases, and we have a couple of places where we can actually use the exponent rules that we know. First of all, we have an exponent raised to another exponent. That means we can multiply those. So now in the numerator we have 3 to the 3/4 power. And in the denominator we have 3 to the 1/2 power. And now that we have a common base, division just means subtract the exponents. So we can rewrite this entire thing as 3 to the 3/4 minus 1/2, all in an exponent. Let's do that subtraction. Well, let's see, that's 3/4 minus 2/4. And our final answer here is just 3 to the 1/4 power. If we happen to want to see that in root form, that's just the 4th root of 3. All right, let's take a look at another example here. Let's use the product property here to split this up into 2 separate radicals. And let's deal with these one at a time. Let's rewrite these with fractional exponents. Well, it seems pretty easy to deal with this term on the right with our variable, because all we have to do is multiply the exponents. And we can simplify 2/4 to 1/2. So we know in our final answer here we're going to have x to the 1/2. But let's deal with that 25 to the 1/4. We've actually seen an example very similar to this just above. Remember that one of our goals here is to reduce the index on any radical to be as small as possible. So if we can turn this 4th root into a 3rd root or a square root, then we've simplified this expression. Well, the key to doing that is recognizing that 25 is itself a perfect square. And 25 to the 1/4 power is the same as 5 squared to the 1/4 power. Now we can do the same thing we did with our variable. So here we have the two factors of the product that we're going to end up with. Product property allows us to recombine these since they're both to the half power. So we have identical indexes here. So that's our solution here, 5x to the 1/2 power. Or, if we want to rewrite it in radical form, it's just the square root of 5x. Let's look at one more slightly difficult problem having to do with just variables. xy divided by the cube root of z. Well, clearly we need to rationalize this denominator. And remember that when we do that, we want to make sure that we get z to the first power in the bottom. That means it's better to think about this with a rational exponent. And that's just z to the 1/3 power. So if I want to get z to the first power in the denominator, I'm going to have to multiply this expression by z to the 2/3. Why is that the case? Because in multiplying z to the third and z to the 2/3, we add the exponents. That gives us z to the 3/3 on the bottom. On the top, we simply do the multiplication. Now the denominator just becomes z, and if we want to rewrite the numerator in radical form, the numerator of the rational exponent becomes the power on z, and the denominator becomes the index of the root we're taking. Hopefully that's enough examples for one video. I'll give you some homework, and you can work on problems just like this.